So section 2 is about non-standard normal distribution. So yesterday we learned the standard normal distribution, which is basically our mean is always 0 and our standard deviation is always 1. Now our mean and standard deviation could be any other number. So it's a lot of review from yesterday, so it's actually not that bad. They do throw in z-score, so we have to remember how to actually calculate a z-score. So that way that's not new information. Yesterday we did say the z-score. This is the distance from the mean. I'm pretty sure that's what we said it was. Now that I'm trying to think back. The distance from the mean. Okay. And it could take on values that are negative or positive. Okay. But our formula, if you remember back when, I don't even remember what chapter it is, but we did do this. We take our data value x, whatever that is, we subtract it from the mean and divide by the standard deviation. That's how we calculate the z-score, and that's helpful when you're comparing data values. So like if you're comparing an ACT score to an SAT score, you can figure out which one's more extreme based on the z-score. If it's a larger number or further away from the mean, then it's a higher z-score, it's more significant. Okay, this also today, it standardizes the data value from a non-standard normal distribution to a standard normal distribution, which is basically what this graph on the bottom is showing. So like today, we have a non-standard normal distribution, which is this first graph. So we can see we have some mean value and we have some data value x, our random variable. So I could standardize this data value so that way it's just a z-score on the graph instead of a data value on the graph. Okay, most of the times we're just gonna stick with a non-standard normal distribution because our calculator actually can handle that. They always had to convert to a z-score because they did not have technology like back in the day. They used like these big tables to actually calculate probabilities in z-scores, and it was so time consuming. You should be lucky that we have awesome technology that we can use right now. It makes the math so much easier. Okay, yesterday we did find areas or probabilities. We understood that the area underneath the density curve is always 1 no matter what. So that means it's like 100% of the probability because the area is 1, so we can make that connection that whatever the area is under the curve, it is the same thing as the probability. So what we were doing yesterday, just to sum up, we were making a normal distribution graph. And I would say to illustrate the data. So today, I want to see the mean in the center of the graph. I want to see wherever the x value is. And then you're shading the correct region to represent the probability. And then step number 2, we always use our graphing calculator. And then we use this normal CDF button. And then, yeah, we'll talk about that. Okay. So today we have the length of human pregnancies are approximately normally distributed with a mean of 268 days, standard deviation of phi equals 15 days. So find the z-score if a pregnancy lasts for 280 days. So this, they're asking for a z-score. They're not asking for a probability, so I don't need to make a density curve, a normal distribution curve. I just need to use my formula to calculate the z-score. So our formula is that fraction, so z equals our data value. Our data value right now is 280. I'm subtracting it from the mean, which is 268, and dividing it by the standard deviation, which is 15. Whatever the heck that is. So I got out 0.80. And remember from yesterday's z-scores, we always round to 2 decimal places no matter what it is. So that's why I put an extra 0 on there, because it has to be 2 digits. Okay, so the next one, same thing, find the z-score So I'm going to use the z-score formula to actually calculate this. I'm not finding a probability, so I don't need to make a normal distribution graph. So same thing, so 261 minus 268 over 15. I got out negative 0.47 when I round. And z-scores can be negative. They can be negative or positive because they're on the left side and the right side of the center of the data, the mean. Okay, find the probability that a human pregnancy lasts at least 282 days. So now it's asking for probabilities. So that means I need to find like the area underneath the density curve. So I'm going to draw a normal distribution graph so that way I could visualize what it's actually asking me. So from the original stuff, I know the mean is 268, so that is the center of my data. Standard deviation is 15, so that's just telling me how spread apart the data is. So 282 is greater than 268, so that's to the right of it somewhere, so maybe right there. So I'm going to put my vertical line. And then when it says at least 282 days, I need to decide, am I shading on the left side of this line or the right side of this line? And we want to be shading all the way over here, I believe. At least 280, yeah. Okay, so then this is where we use our normal CDF button. So in your calculator, we've been going to this distribute key. Same idea, we want to press normal CDF. Okay. They ask for things like lower, upper, mean, and standard deviation. The lower value is based on your graph. So the lowest data value that I'm shading is 282. So that's what I want to type in for lower. My upper, that's everything to the right. So I'm shading to the right. So this value goes like forever, like to infinity. So I want like a number that represents infinity basically. So I basically just type in a bunch of 9s to represent it, and I just say good enough. I don't really know how many 9s I punch in. I just punch in like 8 or 9. And then our mean, they said, was 268. So instead of 0 from yesterday, you have to actually type in the mean and the standard deviation value and then enter through all of it. I got out a probability of 0.175. And remember, probabilities, you always round to 3 significant digits. So that's my third digit there is the 5. Okay. Doing some more, so we have probability again. So I want to graph a normal distribution curve. Oh, that looks sad. Same thing, I want to label it. So here's my mean of 268. That's always in the center of my data. And I want between 254 and 261. So those are both values less than 268. So I have 2 lines to the left of that. So I'll just say this is 254, 261. And I want between that, so I want to calculate the area of this value between, which area is the same thing as probability. So we're doing the exact same thing. So I want to go into normal CDF. Our distribution key, our lower value though, is now 254. From my shaded region, my upper value is 261. Mean and standard deviation are still the same. And I get out 0.145. And then last but not least, still got a probability, so still have a density curve. 268 is my mean, and that's my data value. So I'm going to draw a vertical line through 268. So find the probability that a human pregnancy lasts at most 268 days. So that means I want 268 days or fewer. So this is my shaded region. Technically, I shouldn't need to use my graphing calculator because it's a normal distribution. I know 268 is exactly in the middle of it. So from my graph, I am shading exactly half of this. So my probability should be 0.5. You could type it in your calculator if you want to. You should get out 0.5. I'm actually going to verify because now I don't trust myself. Also, if you're typing this in your graphing calculator, this is a good thing to know. You have a lower bound, so it's going forever to the left. So I need a number that represents like negative infinity. So I type in a negative, and then same thing, I punch in a bunch of 9s until I feel like that's sufficient. Yeah, I got 0.5. Okay, moving on. So now we're kind of going in reverse. So I want to figure out the z-score or the data values from an area or a probability. So same thing. So step 1, I want to draw a density curve illustrating the data. Once I do that, so the only catch with using like areas and probabilities like yesterday, I want to calculate the area to the left, and it always has to be to the left. And this is like kind of a weird aspect. So like if I have a shaded region to the right, then I need to convert it to the left. And then I'm going to use my inverse norm button on my graphing calculator to actually calculate the data value or the z-score. Okay. So SAT scores for each section are standardized, so scores follow an approximately normal distribution with mean 500 and a standard deviation 100. Maximum score possible is 800 points. What score corresponds to the top 10% of students? So I would draw a normal distribution curve since they told me that's what this looks like. I know my mean is 500, so I'm just going to write that in the center. And standard deviation's 100. Maximum score possible is 800 points. Great. What score corresponds to the top 10% of students? So this 10%, this is talking about like the probability of students. So I'm at the top 10%. So if I'm using my normal distribution curve, the top is like maybe here, and I want the area of this curve to be 0.1. So I need to figure out what data value corresponds to that area. But I need to figure out the area to the left of this line because I need to figure out this data value right there. So the area to the left, if I know the density curve is always 1, 1 minus 0.1 is 0.9. So that's the area that I'm going to use in my graphing calculator. So same thing, go to your distribution button. It's your third option down instead of the second option down. My area, I'm typing in as 0.9. My mean is 500. My standard deviation is 100. I got out 628 point, we'll just say 2, or maybe just 628. 'Cause I don't know if SAT scores can have a decimal since that's what we're talking about. So like a score of 628 on your SAT is the top 10% is like the cutoff mark. Okay, moving on. So what score corresponds to the bottom 25% of students? So same thing, my mean's right in the middle, 500. Now I want bottom 25%, so same thing, this is also a probability. Maybe I say a quarter of the data starts there. So this is my area of 0.25, and I need to figure out this data value mark. So I already have the area to the left, so I don't need to like subtract it from 1 or anything. So I'm still using inverse norm. Same mean and standard deviation. I got a data value of 430, and I'm going to round to a whole number, 3. Yeah, okay. That makes sense because that's a value less than 500, like that's the bottom 25%. You'd think 50% of the people are at 500. Okay. Between what two values will you find the central 95% of scores? Same thing, draw my curve here. I got 500 in the middle. So this one's a little more confusing, I guess you would say. It's not like it's terrible over here. I want the central 95% of scores. So basically, I want everything centered around 500. So, but I'm only excluding the 5%, the extreme values. So technically, I want like a cutoff mark there and a cutoff mark there. So that way everything inside of this represents an area of 0.95. So then I need to figure out what's the area left over for like this part and this part. That's what we're concerned about. And there's 5% left, or 0.05 area left over for these two places. So that means the area of this part is half of 0.05. So half of that is 0.025, and this one's 0.025. Why we have to do that is I want this data value and this data value. So then I want the area to the left of these. So if I focus on this one first, the area to the left is 0.025. So I want to find the data value at that point. So still do your inverse norm. So 0.025, I have the same mean as standard deviation. I get out 304, basically exactly. But then if I'm doing a data value to the left of this mark, my area is now a combination of this 0.95 and the 0.025, because that's everything to the left of this. So the area I want to use is 0.95. Oh, I wrote that wrong. 97. Sorry, that's messy. 5. Yeah. So then when I type that into my graphing calculator, yeah, okay, I should get out a data value of like 696 if I round. So these are the two scores that we get for the average of everybody. So I should fall between 304 to 696 on my SAT if I'm in the center 95% of students. Okay, moving on. So our last example, oh, just kidding. We have 2 more. Oh, bummer. Okay, imagine before you entered college, you scored a 26 on the ACT. Your best friends took the SAT instead and scored a 620. ACT that year had a mean of 21 and a standard deviation of 4.2, whereas SAT had a mean of 500 and a standard deviation of 100. Who did better? So this is where like that Z-score comes in handy, because I have 2 different means, I have 2 different standard deviations. It's hard to compare a score of 26 to a score of 620. Like, where's the relevance? Like 26 is higher than a mean of 21. 620 is higher than a mean of 500, so we're both above average, just who's more above average than the other person. So I'm going to find the Z-score for the ACT test and the Z-score for the SAT test. So Z-score, we're starting with our data value, subtract the mean, and divide by the standard deviation. Same thing with SAT, so Z-score or data value minus the mean divided by the standard deviation. I don't know what the other one is. Oh, snap. They're basically the same thing. Okay, so I got 1.19 and 1.2. Technically, who did better is the friend who took the SAT test, because their Z-score is further away from the mean than the other one, because it's a larger Z-score. Okay, critical values. We kind of talked about these yesterday. You saw them as like Z of the alpha. Now we're using it more as like significance. So if they're asking for a significant value, I am talking about like the extreme values. So in our normal distribution curve, we add significance. We're always comparing it to 0.05. That's always been the number we compare our probabilities to. And if it's smaller than this, then I know it's a significantly low or significantly high, because we had these probability statements. Probability of X or more has to be less than or equal to 0.05. Same probability of X or fewer also has to be less than or equal to 0.05. And technically this number could be 0.1 or 0.01, Just the universal one is 0.05. So when we talk about that, we're talking about these extreme tail values. Like those areas are 0.05. So we're going to use this to answer this question. So we know the women have a normally distributed pulse rates with a mean of 74 beats per minute and a standard deviation of 12.5 beats per minute. Identify the pulse rates of women that are significantly low or significantly high. So I could do the range rule of thumb and just make it like 2 standard deviations larger and 2 standard deviations smaller. But I want to try and use this like area and normal distribution curve to figure this out instead, just so we can make the connection. So here's my normal distribution curve. I know my mean is 74, and I want significantly low and significantly high. So I want the bottom 5%, and I want the top 5%. So this area is 0.05. This area is also 0.05. And I want to figure out these data values that make those areas true. So if I start with the bottom one, I want to calculate this guy. So the area to the left is 0.05. So that's what I'm using in my inverse norm. So if I type it in my calculator, I have 0.05. My mean is 74, standard deviation 12.5. I got this pulse rate to be 53.4, we'll say. Okay, but then this next one, this data value, I want the area to the left of this. So I want this whole area combined with the significance value. So this area that I'm using in my calculator is 0.95. So then I want to figure out the data value with 0.95 instead of 0.05. And I got 94.6. So if you had a pulse rate lower than 53.4 and higher than 94.6, then you have a significantly high and a significantly low pulse rate for women. Okay, and then you have your homework assignment. Have fun. Answer key is in Schoology.